Okay, I've finished setting up the next example. So, okay, so step 2, I'm going to introduce the AVX vector, SIMD vector parallelism. So, I changed a few things. So, first of all, I changed the way we allocate these arrays so that they are aligned. So the alignment inside an array is by default, I think it's 8 or 16, and AVX needs your alignment to be 32. So there's a special way of doing an allocation of a variable in C for wider alignment. And it needs to be like this, or otherwise I was getting like a segmentation fault when I tried to access or load or store variables into a not aligned array. So now I've allocated x, y, u, q are now allocated with not the usual malloc, but the malloc, so that you can allocate aligned, and this n align I've set to 32. Okay, and this is just a declaration thing. You need to allocate your memory space in a certain way so that they are aligned. Now, this is just a number that I'm choosing for the number of points. And the rest of the code, you can assign variables in the same way. It's just the first part needs to be changed like that. And now, this is the main part of the code. And now, I'm doing some special operations with these MM256 load and PS, store PS, set PS. Okay, so what this load does is it takes the pointer of x. So right now x plus I, this is still a pointer. So it's the pointer to x incremented by I number of elements. And I is looping over from 0 to, why is it 1/8? It should be, this should be to n. And just the increment is 8. So I'm looping from 0 to n, but jumping in like every 8. And then what this load PS does is it loads 8 numbers starting from this pointer here. So if I put x plus I, and I jumps like 8, then everything in between, it's loading here into this 8 number. So M256 represents like a vector of 8 floating point numbers. And same for x, y, and ui. These are set so that they contain 8 numbers instead of 1 number that it was originally containing. So this is creating the vectors. And the type is called M256 instead of float. And then the rest of the operation is somewhat similar, but instead of doing the plus sign and multiplication sign, I have to explicitly write mul or add, but inside the computer, this is actually closer to what's happening when you write like plus and multiple signs. It's actually doing this as an instruction inside the computer. It's actually, multiplying the two numbers and putting into something before it adds into some number. So this is closer to the actual operations. And in the real code, this is just a sample code, but if I want to really optimize this, I don't want to reuse the same register that I'm using for this operation here and then add it again here. There's more efficient ways to sort of use the register so they don't read immediately after the write. And for example, if I'm doing a multiplication and addition right next to each other, there's another operation that does this in one single operation called the fused multiply add. So for example, I can use such things if I was really trying to optimize. But this is just an example, so I'm not doing those things. Every time I want to load something into dx or dy or R2, if I'm loading a number, I do like a set one. So this xj that I want to subtract from, I need to first load it into a vector. And the difference between load and set1 is that load loads all the different numbers into the 8 vector components. Set1 loads the same number, so xj is just one number. It loads the same number into 8 components of dx. I'm just reusing dx. This really means xj. And so I want to subtract xj from xi, and so I'm doing it with this kind of instruction. And I'm doing basically the same thing that I wrote earlier. And now one important function here is in these AVX instructions, there's something called RSQRT. This actually takes the square root and also does division by that square root. It's called the reciprocal square root, which means the inverse of the square root. So if you put in here r squared, it gives back the inverse of r in one calculation. And this calculation is much faster than a square root and take division operation. So doing this in one go, because mathematically the reciprocal square root has properties where you can expand it and estimate it really fast with very basic multiplication and addition arithmetic operations. So that's why inside a computer, the inverse of a square root can be calculated very fast. And so it uses that operation, and then now that we have the 1 over r, we multiply that to qj with mul ps and then do add ps so that we get the ui. And then finally, we store ui with store ps. This has 8 values of ui, different values. And if you put store, then it stores all those 8 values back into the proper memory space of the incremented u pointer, incremented by I. Okay, so now everything looks a bit complicated, but since the example I'm doing is so simple, it's just a very simple calculation, it's a good way of checking the answer. Again, I'm comparing what I calculate here, ui, with what I've stored here in the variable u and access it with the index I. So if these two numbers are the same, that means I've successfully implemented. And so now I'm adding this number here, like a epsilon squared thing, because I wanted to avoid the zero divide with an if statement. I didn't want to code an if statement into this because it's a bit more complicated. It requires like a bit mask operation. So just adding a small number avoids zero divide. So this is the easy way to avoid that going to infinity. So now let's run this one with this command. So now you need to add, I don't know if your machines support this compiler. If you don't, then I just need to change one thing. And so change this to SSE so that it can run on SSE. And then I need to go back and change everything that says 256 to 128 and everything that says 8 to 4. But it's just, can everyone make sure that they have, I think most modern processors after Sandy Bridge have AVX. So if it's some computer that has been bought in the last 5 years, then you should have this instruction available. Is everyone able to do like well, maybe first of all, they don't have this code. Okay, so I'm going to upload this code to the, so that you can download again. It's a bit longer, so if you try to just copy and paste, you might have a hard time. Oh, it's not here. One moment, I need to, I was working on a different machine, so I had to get the file. It should be appearing soon. Yeah, okay. So I am uploading this to the Google Drive repository now, so you should be seeing it shortly on the website for Google Docs. In the meantime, you can see the code here, but it's hard to show the whole thing. I can just show you just one part of the code. So it might be hard for you to just copy it. Once you're able to download the code, you can execute this following command: gcc parallel to MAVX, and the rest is the same. Just add this dash M AVX so that you use AVX instructions. Okay, so you can see that it's giving the correct answer. The numbers are not exactly the same because, well, first of all, I'm using floating point or floats, single precision. So, these higher digits are not going to match because of the single precision arithmetic. And also that reciprocal square root that I've used has lower accuracy. So you can't get very high accuracy with this answer. Okay, but it's running, and so I want to compare like the speed up between the two. So instead of using time, now I want to time two parts of the code separately. So I want to time this vectorized part, and I want to compare its timing to, like the direct part, for example. And so I'm going to introduce a timer function that I can grab from, again, some other part of my code. So this thing here, get time, is a function I've defined so that I can use as a timer. So to use this, I need to include a file called sys/time.h. And then this header file contains, this is a useful function to have if you're programming in C. This get time of day gives you like a very big number and puts it inside this variable TV, which is of a strange type called the structure of time val. And what it has is it's a structure that contains the seconds inside TV sec, and it contains microseconds in TV usec. And all you need to do, because this is microseconds, you multiply 10 to the minus 6, and you add those two, and you can get a very accurate microsecond order measurement if you subtract. So say you do get time at the beginning, like I will do now, and you can just print these timers. So let me do, I want to time this operation starting from here. So say I do like a tick, get time, and then at the end of this function, I will add, like talk, get time, and then if I print, I just need to print the number here. I subtract the two. Okay, so, and then I do the same thing for here, and I'm not going to print this thing anymore. So I will do like, since I've already defined talk here, if I do like if I do like this and then subtract tick from talk, then I can do tick, talk, and tick to measure the two parts successively. And then I need to change this back to n because I want to do everything. And it's probably going to take a long time if I don't reduce this number. So I'm going to reduce this to like 10 or something. And then, okay, and then I just need to do the same calculation and it will report numbers. Okay, so the AVX part, or maybe I can do a little bit bigger calculation. So let's do like 12. yeah, so now, maybe it's better if I do OpenMP for both loops. So this uses OpenMP, but the top number comes from the AVX execution, and the bottom comes from the bottom number is coming from the sort of plain C code. You can see that the code looked ugly, and I know some of you don't want to code like that, but the difference is this much. It's actually a completely different performance. So you can see why I'm doing this kind of explanation. It's like 20 times faster if you code. And we checked that the answer is correct, so it's doing the same operations. But I'm comparing this thing here, just looping over from end to end, calculating basically UI for the interaction of all of these with the kernel that I've been talking about throughout the lecture. And then this one is doing the same thing, but using, slightly more advanced vectorized instructions called AVX. And it's, it has to load into these intermediate numbers, so it's a bit cumbersome to write the code, but things like this, the reciprocal square root function, which can execute very fast with very few clock cycles compared to the original square root, and the fact that it's processing 8 things at a time. So the loop count, see here, is 1/8 already for and OpenMP can actually parallelize jumping loop indices. So I think it's parallelizing this whole thing, and you can see that this code. Maybe I can clean it up a little bit more, but it's already not so complicated as the one I showed you that was very long. It's not like that yet, but this one is already fairly high performance. You can see this is the effect of vectorization and using AVX. So now we have OpenMP parallel 4, but even compared to this OpenMP parallelized code, you saw that it's very fast. And so yeah, let me run it again, this time with like the OMP num threads, to see how the effect of OpenMP changes the outcome of this run. So see, when I was running with num OpenMP threads 1, by default I set it to 1. So this is using only one thread, so it wasn't actually using OpenMP. But you see, when I combine the effect of OpenMP with the AVX is speeding up as much as the other one is speeding up. So now this is the combined effect. It's now very, very fast. OpenMP plus the AVX speed up is giving me like 0.02 seconds to execute. And then I think because this machine has 4 threads, it will continue to accelerate up to 4 threads. And so now the parallel scalability, the parallel efficiency is not 100%, so it's not like 0.013 exactly like we want it to be, but now it's still doing quite good. And this is not 0.26 either, but it's still doing pretty good in terms of scalability. So now we have a very fast execution, and this is sort of what I wanted you to see in the parallel programming session. We used today OpenMP and SIMD vectorization with AVX. So you can see that this can be used in like most Linux machines. If you have GCC that's newer than 4.3, you can have FOpenMP as an option. And if you're using Intel CPU that's newer than like 5 years ago, then you can use AVX. So this is available on most machines everywhere. It's not something special like MPI, where you need to install MPI and have multiple nodes to execute. This is something everyone can use on their desktop, and it's giving you a lot of speed up for this kernel. So I've today discussed you about GPUs, but I don't think we had time to do the GPU thing. But so now you can actually have a good speed up, and now you know how to measure time. Well, maybe some of you already knew this, but with this timing function, it's very useful. You can just put this in, like it's like you're writing MATLAB code and putting tick and tock. You can actually call this getTime function in any C code and just write yourself like a tick equals getTime and tock equals getTime, and so it will have the same effect. The other things that I had to change was this mmmalloc, but that's just a definition change in the beginning of your code, and most of your code, and also you need to do the mmFree at the end, but that's something like a standard procedure when you want to use like wider alignment for your loads and stores to your wide vectors. Also, the new chips that will be coming out in the future will have 512. So now, like the next generation Skylake chips that will be coming out in the future, like next year and the year after that, will have MM512. And so now, everywhere where we used 8, like this 8, number 8 here, and the alignment number for the, these aligns, you will need to change so that they use a wider vector. And so, so all these numbers that say 256, in the future CPUs, you will have to change to 512. And so these numbers keep getting wider and wider on future CPUs, and that's where actually the performance is coming from for these newer chips. And so if you can't use the 512 on the new chip, your code is already half the speed just by that, and you're not using the full capability of the CPU anymore. And so this vectorization used to be not so important, because before AVX, we had, like half this size. It was 128. And you would only get like 4 times speed up for a floating point. And if you're using double, you would only get twice at most. So it wasn't very much of a speed up, and it wasn't a big deal before. So no one was worrying about programming with these kinds of SIMD intrinsic functions. But it's getting more and more of an advantage. The next generation will have 16 times speed up if you can do this calculation. So now, if you have 16 cores, if you can use OpenMP, it's 16 times faster. And then above that, if you can use the AVX 512, it would be even more 16 times faster than that. That's already 256 times of a difference if you are having a naive code and if you can use OpenMP or AVX. That's a very, very big difference. So parallel computing is not optional anymore. You need to use these features, or your code is going to be very, very, very slow. So this thing, maybe most of you have not heard of until today, but this, as you've seen in the timing results, it's completely different. You get so much speed up if you can use this. So definitely, if you're seeking for performance and if you're interested in like high performance computing, these things you can already do on your desktop. So I think this was a demonstration of the capabilities of parallel programming. Okay, so this one has been uploaded to Google Docs, so you can download and see what is happening inside more closely. Okay, so we have, yes, yeah.
Yeah, to take advantage of AVX, is there some simple way, like there's compiler things?
Oh, sure, yeah. So.
Do we do all that kind of things by ourselves?
Yeah, so let me do an experiment. Let's see. So if this has an Intel compiler, oh no, sorry, I see. Good. Okay, so let me show you some experiment here. So I am going to do, so right now I'm comparing like a hand-tuned AVX with a no AVX. But the Intel compiler has you can use pragma, you know, like a AVX pragma that tells the compiler to do some AVX. So let's say I put pragma SIMD here. I don't know, you know, maybe this compiler version doesn't support this, but I should have checked before, but if I use Intel compiler, it's OpenMP instead of FOpenMP. And so there are these small differences, but let's see if this runs and see how it runs. No, this can't be right. No, something broke, I think. No. Okay, something is being optimized out, it seems, because this does not look like the correct execution time. But so yeah, it's too bad I couldn't demonstrate, but you can do pragmas into the original naive code, and maybe I can search on the web for an example. So okay, so somehow this is in Russian, but yeah, maybe it's because there's a lot of good Intel developers in Russia. They have a very big team, like the MKL. A lot of the MKL, Intel MKL programmers are Russian. So this is something that I can't read, but this I can read. So if you can tell this loop, it's very similar to what we've been doing today. So if you can use this pragma vector aligned and pragma SIMD. You put this here, and then it will automatically generate those AVX add. You know, here it will use AVX. MM256 mul PS, for example, and here it might use the built-in MM256 sign. Operator, and here the mm add ps, and and input it into this register here. So it has like the pragma variants, like OpenMP pragma. You can use pragma SIMD to generate the AVX code, but sometimes the compiler gets confused and cannot generate the proper one. So if you manually do it, you're assured that your code will be fast. But this one, it depends on how lucky you are. So and so it becomes very compiler dependent, and that's why I switched to the Intel compiler to try to check. So Intel compiler for an Intel chip can figure these things out better than like trying to do it with GCC or like a PGI compiler, for example. And so you can first try this one. If it doesn't speed up, then you have to go manual. But first try these kinds of pragma SIMD and pragma vector aligned, because it's easier. And yeah, so this is the sort of short version of vectorized code. And if you want the long version, you need to do this. You need to do this one. But yeah, so the newer compilers tend to do a better job with the vectorization, and especially the one for the Intel Xeon Phi. The hardware is a little bit strange, but the compiler for that does a very good job with that SIMD vectorization stuff. So I think first thing you should try is pragma OMP, and then the next thing you should try is like pragma SIMD and pragma vector aligned. And then, if that doesn't work, just try to do this one. And yeah, so in the later half, we could either try to do a little bit of MPI or GPU. It's up to the environment. But I'm not sure how many. So how many people? Because both MPI and GPU need a computer that has these things, and most computers don't have these things. So maybe we can just stick to some more OpenMP, because we only did it for the simple case, we can do OpenMP for step 1, 2, 3, 4, 5, 6, 7, 8, and maybe AVX, or we can do like GPU or MPI. Who wants to do GPU? Okay, one person. Who wants to do MPI? Okay, so do you have an environment that does these things? Oh, you do. Okay, so let's see. I can do it especially for you later, but for the course, I will stick to the OpenMP for the next, like step 1, step 2, step 3, and proceed in the next hands-on. Okay, so everyone has the step 1 through step 8 in their machine, right? So we just add this one line and see what happens to it, and then time and see. Yeah.
So talk a little more about the AVX thing. Yeah.
Ah, okay. Here?
OpenMP and AVX.
Ah, okay. Yeah, I'll discuss about both for the steps 1 through 8. Okay, thank you.